We are going to construct a world-first mechanical computer driven entirely by kinetic energy and over 3,000 physical components. This is the Chronotheon. It is a unified superstructure where astronomical, temporal, and logic features operate on a single mechanical platform. Executing a build of this magnitude requires strict prerequisites. You will need a multi-million-dollar R&D budget, environmentally sealed cleanrooms, and access to Liga microfabrication machinery. We are moving past traditional watchmaking. We are fabricating a programmable, living physical system where absolute manufacturing perfection is the baseline. Step 1 in our blueprint is managing energy. If you connect a grande sonnerie striking mechanism and a triple-axis tourbillon to a standard mainspring, the system will exhaust its power supply in a matter of minutes. This is the power crisis. To solve this, we will build a central hexagonal power bus to distribute kinetic torque precisely where it is needed. By treating the movement as a bus architecture, we split the watch into independent modular floors, the base engine, underdial module, and caseback module. To feed this bus, we integrate a dual barrel system, completely separating timekeeping energy from the high torque bursts required by acoustic mechanisms. Without this decoupled energy distribution, extreme mechanical complexity simply collapses under the forces of its own weight and friction. Moving to Phase 2, we begin fabricating the 3,100 individual components, holding each to absolute sub-micron tolerances. We use grade 5 titanium for the tourbillon cages, minimizing the mass of these moving parts to prevent parasitic energy loss as they rotate. For the most delicate gears, like the lightning seconds wheel, we use Liga technology to electroform the components, achieving precision thinner than a human hair. For the escapement, the spherical balance spring requires delicate manual heat treatment and physical pinching. This shaping ensures it cancels the effects of gravity, regardless of the device's orientation. The true success of a mechanical computer relies entirely on mastering this material science at a microscopic scale. Phase 3 is where we hard-code computational logic directly into the physical architecture. We start by cutting a 48-month perpetual lever that reads leap year exceptions, alongside a CNC-milled kidney cam that computes the equation of time to track the exact solar position. We integrate the mechanical arithmetic logic unit, 4-bit memory state levers set on sapphire logic bridges and hard onyx cams. Beside it, the planetary differential system continuously tracks the temporal divergence between Earth and Mars time on a single axis. By combining physical memory and differential calculations, these components elevate the device from a passive time tracker to an active analog processor. For the acoustic systems, we must meet strict manufacturing requirements to build the multi-chime Westminster Carillon striking mechanism. Each hardened steel gong is manually filed down, removing microscopic amounts of metal until its pitch perfectly matches a tuning fork. We must also integrate a silent centrifugal governor, a spinning flywheel that regulates hammer speed so the acoustic strikes do not rush together uncontrollably. Once the parts are tuned, we begin Phase 5, the mandatory dry assembly of all 3,100 components. We test the movement entirely without lubrication. This exposes any hidden clashes or excessive friction within the thousands of interlocking gear trains. The entire watch is then disassembled. Every bridge undergoes anglage to create precise 45-degree bevels, removing microscopic burrs, before the final reassembly using carefully graded synthetic oils. Finally, we enter the grand adjustment phase. The device is tested across 6 gravitational positions and a wide range of temperatures to ensure flawless output. This grueling verification protocol is the ultimate barrier between a collection of expensive gears and a functional horological masterpiece. Now we observe the final operational state, a fully assembled mechanical computer actively processing complex temporal and planetary data. The outputs speak for themselves. The chaotic seconds hand snaps cleanly to the signal. The binary bits lock into their memory states, and the multi-axis tourbillon spins flawlessly. This product bridges the gap between centuries-old mechanical horology and modern computer science architecture. The blueprint is proven. Now it is your turn to apply these engineering principles to your own commissions. Review the technical specifications to be